This is a demonstration and explanation to discuss a modern approach to our image compression technology. Fundamentally, this method is based on calculating the eigenvalues and their associated functions to form a basis of solution for the associated integral equations for image compression. We start this discussion off by reviewing the current technology for video These use the MPEG technology, standing for Motion Picture Experts Group. These individuals, this particular website just kind of introduces the background, licensing, how videos are put together, and its history. What is a MPEG? Fundamentally, at this point, we just associate that the MPEG uses the JPEG technology, which mathematically is encoded by discrete cosine transform equations. It's a lossy compression, and we'll cover some of these details when we discuss the JPEG methodology. What is JPEG? JPEG produces artifacts. Wikipedia gives us a reasonable explanation of how JPEG is used to compress images. At any point, you may go to these websites individually and read more of the detail, or you may pause this video and read the data that's brought up. Initially, JPEGs were broken up into 8x8 blocks into the red, green, and blue that normally appears in a color is broken into a Y, a CB, and a CR. And the discrete cosine transformation takes this data and turns it into a series of values. Red, green, and blue are broken into Y, CB, and CR. The I is most sensitive to the Y. The CB and the CR are less eye sensitive, and as a result, these are usually reduced by a factor of 4. In other words, every other pixel is saved and compressed separately. The Y component, since the eye is most sensitive to that, is usually retained at its full 8x8 block. This matrix represents the values from the direct cosine transformation. These are then shifted over a range, and this is explained in this paragraph. This is the equation for the direct cosine transform, and this information then becomes these values. To accomplish compression, of this data. And as a result, this will produce artifacts, which we'll cover in a little more detail. The quantization matrix that they use are these numbers are divided into these numbers and converted to integers. And this data is the actual data that's transmitted. Now, this portion of the direct cosine transform defines the edges of the picture. In this case, an 8 by 8, as the example is given. And the quantization matrix zeroes out the edge definition, and this is what produces the artifacts. Once this is the equation that they use to round off the direct cosine transformation results. And then the data is collected in this form to produce an integer sequence in this with a lot of zeros. So as a consequence, this produces a very small amount of data that's transmitted. On the receiving side, this data, this compressed data, is this compressed data is transmitted. Then the receiver decodes the image, and it's noted that this matrix is close to the original matrix except for the edge definitions. And then the picture is obviously recreated. Here is an example of what the artifacts look like in a JPEG image. This is called a high quality image. This is where the quantization matrix noted above has much larger or closer to 100% values. And then the quantization matrix noted above again, as the quality drops, we begin to see the artifacts appearing, or the lack of edge definition. This would be the edge. To be noted at this point is that these are a constant color. In other words, if this data were transmitted in such a way that there was a color variation, the edge definition could be recreated on the receiver side much more easily. To demonstrate how the data, JPEG data, can be recreated on the receiving side, the individuals at Max Planck Institute came up with a learning technology to remove JPEG artifacts. This paper produces an explanation of how these individuals were able to create a high quality image from a low quality image. As an example of their mathematics and their methodology, they would take the 8 by 8 pieces and, using the difficulties that the direct cosine transform has by going across the 8x8 blocks. They would attempt to derive what the edges would be. Now you'll notice in a couple of cases they would enlarge various portions of this particular image. And the blackness or darkness of the hair is absent when you just simply enlarge the sub-image. So they would recreate the darkness of the color, and as you can see, they did a very good job by using their algorithm of expanding this very low quality or low resolution image in its lack of color to a reasonable representation of an enlarged image. They go on to explain their mathematics and how they interpolate and solve for their equations. This particular graph illustrates the number of basis points and how difficult it is to recreate an exact replica of what an original image would have been. In other words, it takes a lot of data to or points to describe what the original image would have been. It would have been nice if there were a way of transmitting the data such that these dropped off more dramatically. We'll cover this in a little bit later as to how eigenvalues and eigenfunctions can enhance this process. Here's an example of some of the photographs that they used to define what the edge resolution was and what the result is of their enhanced JPEG artifact removal. It's a fairly effective process, and it demonstrates that it is possible to transmit data and recreate a reasonable representation of what the original image would have been. And here's some more examples of their recreation of the edge definition. Remembering one more time that the data for the 8x8 blocks in the photograph from the JPEG are interpolated across the boundaries in an attempt to come up with what the original picture would have looked like. And here's some more examples that are available within this paper to demonstrate how well the receiver can actually recreate the original data, original images that are transmitted. Currently, this technology or a similar technology is not used for image recreation of transmitted data. The next point, what we would like to discuss, is how ostensibly image data is well defined by eigenvalues and eigenfunctions. NASA used the Sojourner rover to capture a picture of Yogi, a rock on Mars. This is the black and white image that's sent back or recreated from this venture. This curve represents the eigenvalues of that image, and we note that these eigenvalues drop off, which means to say that a smaller portion of the image is used to recreate the original image. And here's a motion picture demo of recreation of the image. If you've watched this on television, you would see each of these images coming up on the PCs that NASA was running of the picture as it was being recreated or transmitted back. And at about 40% of the data, the picture becomes quite clear. And about 60% is very, very clear. Again, this illustrates the advantage of the eigenvalue and eigenfunction methodology. For more details on how singular value decomposition works, this is a reasonable website to show that information. What we'll demonstrate next is a prototype code that illustrates piecing various JPEG and bitmap pictures through an approximation of how image compression can be accomplished. Again, what we're doing here is just simply taking an original picture and turning it into an image, then compressing the data, and then redisplaying the image directly. So what will appear on the left will be the original image in JPEG or bitmap format or whatever format it was. Then this will be the compressed image, and this will be the difference between the two. So this is a prototype code, and it has what is called YUV rather than YCBCR. Most of the translating code was pulled down from the internet to save the man-hour cost of producing this demonstration program. And the only code that was available was the YUV component. We could not find some code for the YCB and CR component. I do not know whether this is a JPEG or a bitmap or whatever format. We were not able to put that into the menu box. Now, this is running through the source code, which is not optimized to run very fast. Now, what I want to point out here is that these little blocks of data, and it would be nice if we could expand this, but again, these little blocks of data actually contain a gradation of the data inside each piece, which on the receiving side can be used to recreate the edge definition of the original picture, even better than the original picture would have been transmitted. This is the difference. This is the recreated image. The amount of data that would be transmitted in this case would be approximately 1/8 of the Y component. And because the U and the V component only require approximately 25% of the total data, this would be about 4% of the data because it's 1/8 of. If we sort the data and compress it, this causes approximately a 50% reduction in the amount of data that would be transmitted. And you will note the differences between the images will diminish, and the image will be clearer or more closely approximating it. And this illustrates how the edge information has been transmitted. This is a relatively important point. Sorting the data reduces it further by about 50%. To illustrate how the Y component becomes more sensitive to the eye. This Y component is not exactly the Y component the JPEG uses, but it's close enough for demonstration purposes. You will notice how the eye will pick up an image which is closer to the original image, and the differences again will diminish. This would be without post-processing on the receiving side. So that demonstrates that the Y component is more important, and that the post-processor, or the receiving processor of the data, would spend a little more effort in transmitting or recreating the image on the receiving side. The burger, I believe, is a bitmap. We will, and it illustrates the amount of data, or how the data is actually transmitted to give a definition of the edges, so that the receiving side can again reproduce a very clear image. One point that I wish to make is that this particular algorithm or demonstration is only using an 8x8 block size. We would actually produce an overlap of the information, referring back to the work done by the Max Planck Institute. They did not have an overlap on their block size, so their estimates of the edge definition was diminished. However, an overlap would give you a much better edge definition. Since the amount of transmitted data is considerably less by using our technology, the overlap of the data further reduces the amount of data that would be transmitted, because the edge definition would be much clearer. And the amount of data in the Y component could be even further diminished. Okay, so why did we turn the sort option off? You will note that this block of data contains this reflection from the light source, and that the edges are well defined. In other words, can be recreated on the receiving side. simple sort, of course, reduces the data size by a considerable amount and does produce or make it much easier for the receiving software or receiving side to replicate the image, the original image. As you can see, the slant of the reflection and the edges is better preserved. Again, the Y component will produce an even better representation of the edges. Knows what you can watch the difference and see how Y contributes to it. We demonstrate the lack of clarity from the, I'll run this up to 100%, both of them, it doesn't matter. This image quality does not improve much by the U and the V component. And remember, this is back to 1 on the Y component, so that the blocks will reappear. The sort option is still on. And as you can see, the U and the V component have little to do with the image quality as it's transmitted. So as a result, it can be reduced very easily by 1/4 of its value. We will show, however, okay, excuse me. These are other features that can be used to enhance an actual image or make an image appear to be better than it actually was originally. This is the original image, and again, I'm not sure whether this is a JPEG, a bitmap, or a TIFF, or whatever. By simply sorting the data, reducing it again, we can actually come up with an image that may even look better than the original image. It's sort of like airbrushing the edges, which provides the capability on the receiving side of, see, this airbrushes, or you might think of it as airbrushing the edges. Again, the edges can be reasonably created by the data that's transmitted. The next point that we wish to bring up is, how does our technology work? Our technology is based on mathematics that was invented back in the early days of the hologram, of holography. Holography represents the interference of a known signal or a known picture or a known light source and the interference pattern from an object illuminated by the light source. This was discovered in the 1950s and 60s by using a laser beam, which is a coherent light source. That means single frequency. Run through a beam splitter. Part of the illumination beam hits the object and is reflected off, and then the beam splitter sends the reference image to a mirror, and then the two light sources interfere with each other. This interference pattern is a mathematical equation, integral differential equation, which produces the interference pattern. This interference pattern generally looks like this image here. How is the image, this is a photographic recording of the interference pattern. It may not seem obvious, but this interference pattern is reproduced over and over and over again throughout this image. So how is this different? How is holography different from photography? And these points represent this. The hologram gives you a wide range of angles, whereas a photograph is only a single view. And I think most of you know this. But the important point is, when a photograph is cut into pieces, each piece shows only part of the screen, whereas a hologram is cut into pieces. The whole scene can be seen from each piece. In other words, repeating that, this represents the data of the original three-dimensional image. And any piece of this may be cut out and re-illuminated to return the original image. This offers the opportunity to have a great deal of data compression. It was actually used for recording books into microdots. This shows that same hologram can be viewed from different angles, which is kind of an interesting point, but not applicable to our discussion here. The digitized information from the solution of eigenvalue and eigenfunction equations derived from the interference patterns are then compressed and transmitted. And the major feature here is that the data required for the eigenfunctions is actually reduced by a factor of 3. In other words, from 9 decimal places to about 3. And as a consequence, this data can be further reduced to a 16-character dictionary. This dictionary is the 10 digits 0 to 9. An end of line, a record, row, or column, or matrix would be the number 10. Space or blank as a field separator would be the binary or number 11. Periods or decimal point, which may or may not be required, would be the number 12. Comma would be a 13, a plus sign. 14 and a minus sign for 15. Some of these are not necessarily required, but this is a thumbnail sketch of how the compression would work. A base 3 or 4, depending on how many numbers are used in here, would be a sequential 0 count. and the sequential zero count is included in this 4-bit character screen. You can request or pause this video and read the more details. These are the ASCII codes, which are generally a standard. This is the dictionary, the bit pattern, 0, 1, 2, 3, and 4 bits are required for each of these. This goes into a little more detail. The data that's actually transmitted as the eigenfunctions and eigenvalues would be passed on as matrices or arrays sent to this compression procedure. The matrices consist of 3 basic parts. A matrix header, which is a matrix number, number of rows, number of columns, the data format, and how many places are actually in the number of decimal places that are contained in the matrix. Matrix number is used so that its values may be indexed or recalled or saved by the controller. In other words, the process that's controlling it. Number of matrix rows, matrix columns, data format, 0 to 15. And these are explained here. These are some of the features that the matrix reader and writer can perform elementary or basic matrix element operations while forming and or updating or processing these matrices. This data can preface or contain matrix algebra. So the compression method, this is after all of the data has been passed through the solvers and everything like that to save and transmit the data. There will be codes that would be stuck in front of this, and this would be again based on how the controller wishes to identify the matrix numbers and so forth like that. And these details are not here. This sort of outlines how the compression process works. Data in the form of the integers are passed according to the defined table, and here's an example of how the SLZW compression scheme works. Let's consider these were the actual transmitted bits from 0 to 15 again as hexadecimal numbers. In other words, like this. Supposing that was the bit patterns that we wish to. These would have 4 bits each, rather than in ASCII that would be 8 bits because it takes 8 bits to describe a character. And this illustrates each piece and how the bits go together, and this explains a little bit more on let's see, and this goes on, and the main feature of this right here, this part of coding process is a sequential method, as most of them are. In other words, nothing is known until it's collected, examined, or compared, found, or matched from the input stream. this process is applied twice. The second part of the process is only applied twice, even if there's not a distinct advantage to it. And this explanation goes on to explain that. Once the SZLZW is applied twice with two different dictionary sizes. The first dictionary size is, of course, 4 bits. The second dictionary size is run several times and compared for any amount of compression that's possible by going from 4 bits to 8 bits to 16 to 32 and 64. This is a fairly fast process. PKZip has employed this process since the 70s and 80s in its existence. And it's very fast, so there's little or no time involved in running through this format. Okay, once that first part of the compression algorithm is put together, it is then passed through what might be called the arithmetic compression algorithm. Now, most arithmetic compression algorithms spend a lot of time and inefficiency on constantly sorting the most frequent characters that are passed through. And our approach to that is simply to, as the last of the compression on the first part is found, the frequency is saved, and its coded relationship is passed on to the decompressor. And that saves a considerable amount of processing time. It's generally known that the arithmetic coder is very, very slow. Okay, so again, if you want to read more details of the compression methodology, pause this video, or and SLZW stands for Seth's, that's me, least size data words. Okay. So how would this be put together? Well, an initial implementation of this methodology would result only in less transmitted data with the same quality of image. It would give us a foothold into it. The sending side, we would read the current data format, which would be JPEG or one of its derivatives. It would then be, the data would then be converted to images, as we did in a demonstration program. Then the mathematical interference compression methodology would be transmitted. On the receiving side, our transmitted data would be converted back to data images. Then that data would be converted to the accepted display format, JPEG or its associated MPEG-4, whatever. And then that would fit within the software, hardware, chips that were available on the display equipment. Either way, the data or the image could be enhanced at this point In other words, we could, when converting it to the accepted display format, we could increase the size of each JPEG image, because remember we've transmitted back here the edge definition by either overlapping the images or it's inherent in the process. Future releases would process the images directly and greatly improve the image quality with better or actual edge definition, color distribution, and so forth. And we would replace the software and their associated chips on either or both the sending and receiving sides. And this concludes the discussion of a modern approach to image compression technology.